So we have Physics PhD qualifying exam practice problem number 27. So let's begin, and this is in the quantum mechanics domain. So we have a particle of mass m scatters off the central potential, where v of r equals negative v naught e to the negative r over a, where v naught is greater than 0. For part A, derive the radial Schrodinger equation. So this is a scattering theory and phase shifts problem. So for part A, the radial Schrodinger equation, we have psi of r theta phi equals u sub L of r over r, y sub Lm of that theta comma phi. So the radial equation is negative h bar squared over 2m. And then we have this second derivative here of u sub L with respect to r plus bracket v of r plus h bar squared L parentheses L plus 1 close parentheses over 2mr squared close bracket times that u sub L, and that equals E u sub L. So that's for the radial equation. And with E equals h bar squared k squared over 2m, this becomes u sub L double prime plus bracket k squared minus L times L plus 1 over r squared minus 2m over h bar squared v of r bracket u sub L equals 0. And since v of r equals negative v naught e to the negative r over a, u sub L double prime plus bracket k squared minus L times quantity L plus 1 over r squared plus 2m v naught over h bar squared e to the negative r over a bracket times u sub L, that equals 0. So that's for letter A. Moving along now to letter B. So letter B here, what they want for letter B is using the Born approximation, calculate the differential scattering cross-section. Okay, so Born approximation cross-section, Born scattering amplitude. Here's f sub b of theta equals negative 2m over 4 pi h bar squared times this integral e to the negative I q dotted with r v of r d cubed r, where q is equal to the absolute value of q vector equals 2k sine sine theta over 2. Our potential is central, so the integral here of e to the iq dotted with r, v of r d cubed r, that's going to equal 4 pi times the integral from 0 to infinity r squared v of r sine qr over qr dr. So we're going to use v of r equals negative v naught e to the negative r over a, and then integrating from 0 to infinity r squared e to the negative r over a sine qr over qr dr equals 1 over q integral times the integral 0 to infinity r e to the negative r over a sine of qr dr. Then from there we have integral from 0 to infinity r e to negative infinity r sine of qr dr. That's equal to 2 alpha q over quantity alpha squared plus q squared, quantity squared. Alpha is equal to 1 over a, so 0, so we can integrate from 0 to infinity r squared e to the negative r over a sine q r over qr. Sorry about that, that's a q. So sine q r over qr dr, and performing the computation we get 2 over a divided by the quantity q squared plus 1 divided by a squared, that whole quantity squared in the denominator there. So integral e to the negative iq dot r v of r d cubed r, that equals negative 4 pi v naught times 2 over a divided by the quantity q squared plus 1 over a squared squared. So f sub b of theta, that equals negative 2m over 4 pi h bar squared times the quantity bracket negative 4 pi v naught times 2 over a over quantity q squared plus 1 over a squared squared. So f sub b theta, that equals 4m v naught over h bar squared a times 1 over q squared plus 1 over a squared, that quantity squared. And equivalently, f sub b of theta, sorry, that's a theta, equals 4m v naught a cubed over h bar squared times 1 over quantity 1 plus a squared q squared squared. And our q value is going to be equal to 2k sine of pi over 2, of theta over 2. So q is 2k sine theta over 2. So our differential cross-section is d sigma over d omega equals the magnitude here of f sub b theta squared. And that equals 4m v naught a cubed over h bar squared. That whole quantity squared times 1 over 1 plus a squared q squared raised to the 4th. So here we're going to get our derivative here, sigma with respect to omega, that equals the quantity 4m v naught a cubed over h bar squared, quantity squared, times 1 over the quantity 1 plus 4a squared k squared sine squared theta over 2 raised to the 4th. Okay, so that's part B with the Born approximation. That's the differential scattering cross section, and now we go to part C. So part C, what they want us to do for part C is determine the low energy S wave scattering length. So the low energy scattering length, at low energy, f of 0 is about negative, f of 0 is approximately negative a sub s, and in the Born approximation, f sub b of 0, that equals 4m v naught a cubed over h bar squared. So our a sub s Born equals negative 4m v naught a cubed over h bar squared. And the negative sign is physically sensible for a weak attractive potential. So that's part C. Moving along to part D. For part D, they want us to use partial wave analysis and derive the following relation. So they want us to derive, just going back to this relation here, f of theta equals this sum L equals 0 to infinity for this 2L plus 1 quantity times e to the 2I. That's a delta, sorry about that, delta sub L minus 1 over 2ik times p sub L cosine theta. Okay, so just going back here to letter D, partial wave expansion, the asymptotic radial wave function behaves as u sub L r approximately or proportional to, or about, I'm sorry, is a sine of kr, or we could say scales to sine of that kr minus L pi over 2 plus delta sub L, okay, or similar to, so psi of r comma theta, similar to this e to the ikz plus f of theta e to the ikr over r. The scattering amplitude can be expanded as f of theta equals the sum of L equals 0 to infinity of 2L plus 1, that quantity f times f sub L, p sub L cosine theta, where f sub L equals e to the 2I delta sub L minus 1 over 2ik. So we're going to wind up with the following here. F of theta equals this sum L equals 0 to infinity of this 2L plus 1 times e to the 2I delta sub L minus 1 over 2ik PL cosine of theta. Okay, and for part E, they want to show how resonance behavior emerges when a quasi-bound state forms. So for part E, and pardon me if I mispronounced anything in part D, I went through that I'm going through this rather quickly so you have this as a reference, but the math and the explanations work out. So part E, haven't had enough coffee today. Part E, resonance behavior. A resonance occurs when a phase shift passes rapidly through. Delta sub L E is approximately pi over 2. And near a resonance energy E sub R, one can write here D sub L E is approximately delta sub L BG plus here tan, inverse tan of this gamma over 2 over E sub R minus E, where this capital gamma is the resonance width. So the partial cross-section is here. This sigma sub L equals 4 pi over k squared times quantity 2L plus 1 sine squared delta sub L. And at resonance, delta sub L is pi over 2. Sine squared delta sub L is 1. So our sigma sub L max is 4 pi over k squared times that quantity 2L plus 1. And we could say physically, the attractive potential can temporarily trap the particle in a quasi-bound state before it escapes, producing a sharp enhancement in the scattering cross-section. Okay, so that's all for this one. Thank you very much and have a great day.